Okay, we're on 4.1, the concept of solubility. Let's take a look at the warm-up. Classify solutions of the following solutes as ionic or molecular by putting a check mark in the appropriate column. Potassium phosphate. Ionic. Ionic is a cation with an anion or a metal with a nonmetal, right? Xenon hexafluoride. Molecular. Phosphoric acid. This one, okay, acids are made of nonmetals, right? Okay, but acids also are made of a cation with an anion, aren't they? Because hydrogen is a cation, and then they usually have an anion that's a polyatomic ion or a single nonmetal. So I guess we could say to some degree acids and bases are going to be ionic to some degree, right? So you can check ionic. I'm just going to leave this one blank, okay? Sulfur dioxide. Molecular. Ammonium sulfide. The ammonium ion is a cation.
Oh,
Ionic. Okay. Describe a simple test and its results to determine whether a solute is ionic or molecular. Simple test. Maybe a conductivity probe. What conducts electricity? Ions. Which ones contain ions? Ionic compounds. Okay, so for this one, I would say get a conductivity probe and take your solution and put the electrodes in the solution, and if the light bulb lights up, it's ionic. You have freely moving ions. So you would want to test for conductivity, okay? Because molecular compounds do not have freely moving ions. They will not conduct. Speaking of conductivity, let's go to the electrical conductivity section. Okay, so here, let's talk about what an electrolyte is. An electrolyte is going to conduct electricity. We can have weak electrolytes, we can have non-electrolytes. Weak electrolytes would be things like weak acids and weak bases. A non-electrolyte would be a molecular compound because they do not form ions in solution. Okay, so conductivity is dependent upon freely moving ions in solution. The more ions I have, the better the conductor, the stronger the electrolyte. Make sense? Okay. Ionic compounds down here. Ionic compounds are made of a metal with a nonmetal or a cation and an anion. Remember, if you ever see the ammonium ion in a compound, it is a cation. Therefore, a compound containing the ammonium ion, which is NH4 plus 1, is ionic. Salts are ionic compounds. Salts differ in their abilities to dissolve in water. Salts that dissolve in water will produce electrolyte solutions because they will have freely moving ions. So salts that dissolve really, really well in water will have a very high concentration of ions, and those salts are called strong electrolytes. So it says that right here. Salts that dissolve in water well can produce solutions with high ion concentrations, and they are called strong electrolytes. Molecular compounds do not form ions. They will stay in molecule form in solution. Examples would be things like sulfur dioxide, chlorine molecules, or methanol. Okay, these will all stay intact and they will not conduct electricity. What if I'm talking about strong acids and strong bases? Well, if you go to the next page, here we have listed some strong acids HCl, HBr, HI, HNO3, H2SO4, HClO4. Strong acids will be 100% ionized in solution. They will be great conductors of electricity. What if I'm talking about weak acids? Weak acids aren't going to form ions very often, less than 1% of the time. Since they have very low concentrations of ions, we consider them to be weak electrolytes. So these include things like acetic acid, which can be written a couple of different ways. This is probably the way that you're used to seeing acetic acid written. They also write it as CH3COOH. You have phosphoric acid, hydrofluoric acid, carbonic acid. Recall, carbonic acid will decompose into carbon dioxide and water immediately because it is unstable. And then you have nitrous acid. Make sure you know the strong versus the weak acids, okay? Okay, let's take a look at the quick check. Are all salt solutions strong electrolytes? Do all salts dissolve the same in water? No, so this would be no. They couldn't all be strong electrolytes because some of them are going to dissolve very, very well and some of them will not. So some salts are weak electrolytes, okay? And that's because they don't dissolve to a significant extent in water, okay? Number 2, classify the following as ionic or molecular in solution. A, octane, which is C8H18, molecular. B, trisodium phosphate, a common cleaner, Na3PO4, ionic. Chalk, calcium carbonate, ionic. Sulfur dioxide, a pollutant from heavy industry, molecular. Hydrochloric acid, the acid present in your stomach, ionic. Okay, any questions on differentiating between ionic and molecular compounds? Yes?
Acids are usually ionic.
Acids will form ions. It's just to what extent will they form ions. I'm probably not going to ask you to differentiate between an acid being ionic and molecular on a test. If I give you a multiple choice question, it's going to be very, very straightforward. Like, ionic compound will either be there or it won't. Okay? Okay. Let's take a look at number 3. All right, the SI unit for electrical conductivity is Siemens. A student tests the electrical conductivity of carbon tetrachloride, which is CCl4, tap water, and seawater. The results are tabulated below. Identify samples A, B, and C. Okay, sample A has pretty minimal conductivity. Sample B has none. Sample C has a lot. Which one do you think sample C is? Seawater. Why would you say that? Yeah, because it has salt dissolved in it, and salt is going to produce freely moving ions when dissolved. What do you think sample B is? Carbon tetrachloride, because carbon tetrachloride is a molecular compound. It will not produce freely moving ions in solution. How about sample A? Tap water, because there are a few things dissolved in tap water, so it would be a poor conductor, but it would have like minimal conductivity if you went to test it. Questions on that? Okay, let's take a look at concentrations of ions in solution. when you put something in water, it is typically going to be attracted. If it's ionic or if it's polar, it's going to have attractions to the negative and the positive end of water. Water is polar, the oxygen end has a partial negative charge, the hydrogen end has a partial positive charge. So when we go to put something like sodium chloride into water, sodium chloride will dissociate to form a sodium ion and a chloride ion. So anytime you have a substance, ionic substance, dissolving and separating into its subsequent ions in solution, we call that dissociation. So the sodium ion will be attracted to the oxygen end of water because that's the negative end, and then the chloride ions will be surrounded by the hydrogen end of water because that's the partial positive end, right? And opposites attract. Okay, so what we're going to practice doing is writing some dissociation equations for some aqueous solutions. So these are ionic compounds in water, and we're just going to separate them into their ions. So you tell me, what is the chemical formula for calcium chloride? CaCl2. Good job. Okay, so if CaCl2 is in water, what ions will form? What's the first one? Ca. What's the charge on it?
+2.
+2. And then what else? How many chloride ions? 2, because you have a subscript 2 here. So don't forget that when you go to write those ions on the product side, you have 2 chloride ions. Does this make sense? Yeah.
Wait, isn't that a diatomic element?
But it's not a pure like molecule.
Oh, okay.
Okay? So we're writing these in ion form, and there's no such thing as like a Cl2 ion, if that makes sense. Okay? All right, should we do one more? Okay, let's skip number 2 and let's go to number 3. We have sodium phosphate. What's the chemical formula for sodium phosphate? PO4. Good job. It's been a while. It's been a while. Okay? So this is sodium phosphate. If I'm going to write the ions on the product side, how many sodium ions do I have? Yeah, you have 3. And the charge on the sodium ion is a +1. If I don't have parentheses around phosphate, how many do I have? 1. So I have 1 phosphate ion, and that's it. I'm done. Questions on writing dissociation equations? Okay. 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 Let's go to the next page. It's been a while since we've calculated molarity. So let's just review how to do this. When you're calculating molarity, it's moles of solute per liters of solution, right? And molarity is abbreviated with a capital M, right? And then you have the molarity triangle if you want to use it, okay? What we're going to be doing is we're going to be calculating the concentration of ions in solution. So you'll be given typically the original concentration of the solution. You'll write a dissociation equation showing what ions are present, and then you will calculate their concentrations. Okay, so I'm going to show you what this looks like. Let's take a look here in this example with calcium chloride. Here we have a calcium chloride solution. Its concentration is 0.041. The dissociation equation shows a calcium ion and 2 chloride ions. So if I asked you to give me the concentration of these ions, you would look at the original solution. If you only have 1 calcium ion, 1 times 0.041 would be 0.041 molarity, okay? For the chloride ions, I have 2 of them though. So you would take 2 times the original concentration, you would get 0.082. Easy enough? Everyone can do this, right? so let's take a look at the quick check. We're going to calculate the ion concentration of each solution. So I'm going to do an example for you first. Okay? We're going to skip 1A and we're going to go to 1B. We've got 2.5 molar aluminum chloride. The chemical formula for aluminum chloride is AlCl3. This is going to form an aluminum ion and 3 chloride ions. Do I have you so far? Yes.
Do you have to always write the AQ?
You should. Thank you for reminding me. I have 2.5 molarity AlCl3. What would be the concentration of my aluminum ion? 2.5, because I only have one of them. Agreed? What would be the concentration of my chloride ion? How'd you get that? Yeah, 3 times 2.5 is 7.5 molarity. Okay? What if I said to you, I want the total ion concentration, because it says that up here. If I want the total ion concentration, then wouldn't I add this and this together? Okay? So the total ion concentration would be 2.5 plus 7.5, which is 10. Questions for me? Okay. Do you want to try one of these on your own? Okay. Let's go ahead and take a look at, let's just do 1A. Okay. We don't really do oxalate very often. In fact, I don't know that we've ever done oxalate. So why don't I help you with the chemical formula for sodium oxalate first, and then I'll let you run with it. You know that sodium is Na+1. Oxalate, I believe, is on the bottom left of your periodic table.
Yeah.
C2O4, -2. So Na2, C2O4. Okay. Do you want to take it from there? Okay. Okay, so sodium oxalate, you have 2 sodium ions, so you should have taken 0.45 times 2. You got 0.9. The oxalate ion, since you only have one of them, would be the same concentration as the original solution, 0.45. The total ion concentration is 0.9 plus 0.45. You should have gotten 1.35. Okay, let's turn the page. Okay, sometimes you mix 2 solutions together, which changes your total volume. Okay, so you're really diluting a solution, and what I'm going to do is I'm going to show you how to calculate ion concentrations if you mix 2 solutions together. Okay, so I'm going to go ahead and skip the sample problem, and I'm going to show you how to do it here in 1B. Okay? Okay. Actually, instead of 1B, why don't we take a look at 3? I think 3 would be better. Let me make this a little bit bigger for you. And bring it up here. Okay. What are the ion concentrations in a solution made by mixing 50 milliliters of 0.22 molar ammonium sulfate with 25 milliliters of 0.45 molar ammonium sulfide? So I have two different solutions that I'm mixing together. A lot of times they're gonna have some common ion in them. So that means you'll have to add those ions together in the end. So let me show you what I'm talking about. For the ammonium sulfate, I'm going to take my molarity and I'm going to write it like this. 0.22 moles over a liter. And this is for ammonium sulfate. Okay? What volume did I add of ammonium sulfate? 55 milliliters. Since this is in liters, we're going to convert 55 to milliliters, which is, 0.055 liters. Okay, so this number here is the volume of the ammonium sulfate. Okay, I'm going to put that over the total volume of the solution, which is 55 plus 25, which is 80, right? So 55 plus 25 is 80 milliliters, which would be 0.080 liters. Do I have you so far? So I have the molarity written as moles per liter times the volume of this specific solution over the total volume. Okay. And we're doing this because we're trying to get the concentration. Somebody grab a calculator for me and calculate that. I think I already 0.15?
Yeah.
Okay, let's do 0.15 molarity. This is for your ammonium sulfate. Okay? Now, doesn't ammonium sulfate form two ammonium ions and one sulfate ion when it breaks down? So when this breaks down, if I'm going to get two ammonium ions and one sulfate ion, then what would the concentrations of those ions be? Wouldn't this just be 0.15? Because I only have one of them. And then this would be 2 times 0.15, which is 0.3. Agreed? Okay, now I have to do the same thing with the other solution. Okay, so if I have 0.45 moles per liter of ammonium sulfide, what volume of ammonium sulfide did I add? 25, make that 0.025 liters. The total volume of the solution was 0.08. So this is 0.14. Okay, so we have this up here. Now we have this down here. Are you with me? It's just double the work because you mix two solutions together. Okay? How many ammonium ions do I have here? 2. And then you have one sulfide ion. So 2 times 0.14 is 0.28. And then you'll have the same concentration of sulfide ions. Okay? So if I asked you what the individual ion concentrations were in the solution, this is your sulfate ion concentration. This is your sulfide ion concentration. But then if you want the ammonium concentration, don't you have to add these two together? So you have to take this number and this number and you have to add them so you can get the total ammonium concentration. So this would be 0.3 plus 0.28, 0.58. Okay, that's as long as it's going to get. You'll have one of those for homework. That's it. Okay? Questions on how to do this?
What, 0.080 because you added 55 milliliters of 25 milliliters?
This and this.
So you mixed them.
Yes. So that's your total volume. Right here. 55 and 25 mils is 80 mils. Okay? Okay. Yeah, I have two more things to talk about. Do you need a second? You can take down all those pink signs. And then, yeah, the goggles can go, and those can go there. And thanks. Okay, next page. All right, we're on saturated solutions and solubility. So when you make a solution, you have to dissolve a solute in a solvent, and the amount of solute that you can dissolve depends upon the substance you're using and how much solvent is present. So this brings us to solubility. Solubility is the amount of solute required to make a certain volume of saturated solution. What is a saturated solution? A saturated solution is when you're going to have some solute dissolved, but a little bit of solute will remain undissolved at the bottom of the container typically. Okay, so you're going to have some undissolved particles. And we've got different units for solubility. We've got molarity, grams per milliliter, parts per milliliter, grams of solute per 100 grams of solvent. We generally tend to focus on molar solubility, which is a unit of moles per liter, or molarity. So in these practice problems, when they ask you for the molar solubility, they're really asking you for moles per liter, which is molarity. And this is what you'll be doing on a homework problem, okay? These are just unit canceling problems. So if you take a look at practice problem number 1, it says the solubility of manganese 2 sulfide is 4.7 times 10 to the negative 6th grams per milliliter. Well, don't we know how to convert grams to moles? So if we have the molar mass of manganese 2 sulfide, we could convert that to moles, yeah? And we can also convert to liters if we convert using the power of 10. So 1 milli is 10 to the negative 3 liters, right? So milliliters will cancel there, grams will cancel here, and you'll end up with moles per liter, which is molar solubility. Okay, the molar mass of manganese 2 sulfide is 87.01. I already did it for you earlier, okay? You're going to divide, you're going to end up getting 5.4 times 10 to the negative 5th. Something you can do? Totally, okay. All right, one last thing. Let's go to equilibrium in solutions, and we'll end on this, okay? Equilibrium in solutions means you are simultaneously converting solid to, you're dissolving solid and you're forming ions, and the ions are recombining to recrystallize and form solids. So this is a forward and backwards process, hence the double arrows here. So you'll have your solid here when you're at equilibrium, and then you'll have your ions over here, okay? So this is essentially the same thing as what we were doing with dissociation equations. The only difference is you're going to have a solid on the reactant side, and you'll have a double arrow, okay? So in the quick check, if I ask you to represent the equilibrium present in a saturated solution of zinc carbonate, you would write the chemical formula for zinc carbonate, and you would have to write solid after it. And then you would have a double arrow, because we're at equilibrium. And then you will have your ions. I have a zinc ion in solution, and I have a carbonate ion in solution. Easy enough? Do you need to do one on your own, or we got this? You want to do one? Okay. Take a look at the second one, the aluminum hydroxide. Okay,